Hello, we are Hyperxite, SpaceX Hyperloop pod competition team at UC Irvine, and we're trying to build the future of affordable and sustainable transportation. My name is Johnny Pham, and I'm the chief engineer this year.
I'm Daniela Jimenez, I'm the project manager.
And I'm Susie Nguyen, the electronic system engineer.
So a little bit about the Hyperloop concepts. The Hyperloop concept was proposed by Elon Musk in 2013 in his Hyperloop Alpha white paper. It has the potential to transport passengers from LA to San Francisco in 30 minutes, and it does so by traveling at 760 miles per hour in partial vacuum. As you can see from this diagram, it is very energy efficient compared to other modes of transportation and has the possibility to be the fifth mode of transportation. So a little bit about our team. In 2016, we attended Design Weekend and got fifth for overall design. In 2017, we attended Competition 1 and were one of the top 29 finalists. In 2017, we attended Competition 2 and were one of 6 teams to run in the 2. And for Competition 3 and 4, we were one of the top 22 finalists to attend competition. So our goal and objectives for this year is to research, design, build, and validate a scalable self-propelled pod to demonstrate the feasibility of Hyperloop design concepts at a high pace of innovation. This year we won't be attending competition, but we'll be building our own pod independent of the SpaceX competition. And our objectives for this pod is to have real-time pod behavior monitoring, pod state data logging into comparison against models, and complete a safe pod run at the test track. So this shows how our team is broken down. In addition to us three, we have an undergraduate advisor in management, and we also have various subsystems, so dynamic structures, static structures, braking, pneumatic, simulations, power systems, controls, outreach, operations, and manufacturing.
So here you can see a breakdown of our subsystems based off of the PodCat. So you can see here the braking system along with the pneumatic system that actuates the brakes is centered. And then we also have stabilization wheels all throughout. And then our structure here is the aluminum beam chassis. And then our propulsion will have 2 motors.
Just going into a little more depth about the structures team, for the chassis, we designed an aluminum structure that integrates with the different subsystems with extra strengthening and cutout designs in places, as you can see with these L brackets and these faceplates. So currently we're collaborating with all the other subsystems to finalize designs and begin running in-depth simulations to validate our whole structure's design. We still have to research components within our budget for manufacturing. So we were thinking of replacing the aluminum beams with extrusion beams instead. For our stabilization team, we designed a lateral, vertical stabilization unit that featured a urethane wheel and coilovers to kind of compensate for the shocks due to track irregularities that come from bumps. So currently we're still redesigning based on cheaper alternatives because the wheels modeled here costed the team $6,000 last year. So to do still, we are conducting a modal and structural simulation to validate all the structures for a minimum safety factor of 2. For our braking subsystem, we designed a system that utilized air cylinders to provide 2,350 newtons of braking force, and that equates to 3 Gs of deceleration for our pod. So we're conducting materials research to narrow that brake pad material. We've narrowed it down to ceramics. Currently, we're still looking at different actuators to better fit our design criteria. To do so, we are looking into linear guide rails that will resist the shear loads that come from the braking force. For our propulsion team, we decided to use 2 Leonard 3080 motors. We designed a new motor mount and a wheel clamping mechanism to use tension springs to apply that necessary downforce that we needed. Currently, we're still optimizing weight and dimensions for that motor mount, and we're looking into more bearing and bearing mounting options. So to do still, we need to run through testing on the Leonard motors and to run topology optimizations on the motor mounts to save weight.
So for pneumatics, for the accomplishments, we've been able to complete designing a couple of hardware items. So for example, we have been able to decide on the Luxfer M06D air tank with a maximum working pressure of 2,000 psi. and we'll also be using a 5-2 normally open solenoid valve to actuate our redundant pneumatic braking system. And we've also been able to work up our pneumatic braking system schematic here, which includes a manual valve, exhaust vent valves, multiple pressure transducers, a relief valve, and so they've been implemented for many safety measures. Currently, we need to finalize components and their requirements, as well as their volumetric flow rate calculations. And to do, we need to research piping solutions and components to match system requirements within our budget. For power systems, we've been able to use Altium Designer we've been able to learn Altium Designer through creating individual PCB designs. And currently, we've been creating a basic circuit diagram for the pod, which includes two 12S batteries in parallel for each motor. And we need to research the different specifications for the low power sensors. And to do, we'll continue using Altium Designer to design the PCB connecting all of the low power sensors, and we need to find a battery for low power, which would fall approximately between 12 volts and 24 volts. As for controls, we've narrowed down the microcontroller that we'll be using to the BeagleBone Black, and currently we're testing individual component interactions with the BeagleBone for data acquisition, so all of our sensors, and we will be developing communication between the host computer and the BeagleBone over TCP using the Ubiquiti Rocket M900, which is basically how we communicate to the pod wirelessly. And to do, we will develop software to run on the microcontroller and refine the graphical user interface. So this is our timeline for this year's pod. So in order to have our pod be able to run during the spring design review, we wanted to complete testing by June 5th of 2020. And then, so that means that we have to have the first generation of our CAD done by January 4th of 2020, and then we'll also begin assembling the pod around February 28th of 2020.
That concludes our presentation on our progress so far, and thank you.